All right. Sorry about that. Excuse me. All right, so the 20 kilogram mass is heading in some direction, and I just, because I wrote it down first, it's going to the right. And the other one is a 30 kilogram mass going to the left. Initial velocity of negative 5 meters per second. So the negative is just a directional thing, so it's 5 meters per second to the left. And this is 10 meters per second going that way. All right, so when you're dealing with work, because that's the last one, how much work did box A exert on box B? I have to assume that you've at least watched the video. Whether it's sunk in or not is a different question. The fact that there's two different kinds of work because there's two different kinds of force. Or I guess we can, this is related to the conservative force and this is related to the non-conservative force. So if conservative work is done, then we'll have a transfer of energy from one form to another. So kinetic to potential energy, or potential energy to kinetic energy, or something along those lines. If non-conservative work is acting, the energy is being transferred from one object to the next. And then in that vein, there were the three work energy relationships. The fact that the total work is equal to the change in kinetic energy. The conservative work is equal to the negative change in potential energy. And then the non-conservative work is equal to the change in energy. So that's the three work energy relationships with the, in essence, kinetic energy, potential energy, and this energy right here known as mechanical energy. And just a quick check, what kind of energy is not considered mechanical energy?
Gravitational, Earth's gravity. I have a word day.
Gravitational potential energy is considered mechanical.
Oh, rest energy?
That's the third one. Because it's either kinetic, potential, both of those are lumped into this type of energy. This E right here is just kinetic plus potential energies. So therefore gravitational potential falls into it.
Okay.
Rest energy is the other one, which is not an issue in classical mechanics, which is what this is right now. So rest energy rears its ugly head when you start getting into relativity. All right, so back over to the question over here. So the first question was how much kinetic energy was lost? Well, that's just, you find the total kinetic energy to start with, you find the total kinetic energy afterwards, final minus initial. Let's see, after the collision, they are moving the same, so they basically are stuck together. So afterwards, it is a 50 kilogram mass traveling at 1 meter per second in the same direction that 20 was going beforehand. In this type of collision, there's absolutely no mention of any change in height, of any conservative force involved, and so it is, did I state it explicitly? They say heading towards each other. It is generally assumed in a problem like this that we're not dealing with any change in height. So all the work being done there is non-conservative. And so if you want to know how much work was done by the first box on the second box, all you have to do is look at the change in energy of the second box. So for C, how much work did A exert on B? Well, the amount of work A exerted on B should be equal to the change in energy of B. So it started out at 5. Oh, this will be great if this works. I'm about to ask you for the formula. The one formula you should know. What's the formula for kinetic energy?
1/2 mv squared.
Not the course of angels I was hoping for. Next time. Though I do appreciate those who did. It was unison of 3 or 4-ish. So you got the kinetic energy of that beforehand, and then afterwards, it's going 1 meter per second, so you know, whatever the difference is there. It slowed down, so there was a loss of energy. They both slowed down, they both lost energy. Does that answer?
Kind of, for the final, is there a change in mass, because are they stuck together now? Or are we just considering B still by itself?
I'm so used to the momentum problems. In a momentum problem, the fact that they're going the same velocity afterwards indicates that they're traveling together, so for practical purposes, they're stuck together.
Okay.
However, in terms of the work done on B, yeah, you probably would treat it as, I got my 20 here and I got my 30 here, and so you would treat 30 as the mass.
Okay. Can I have my paper back?
Okay. Yep. And this would be an example of a perfectly inelastic collision. All right, other questions?
I have a question.
Yes, ma'am.
For the conservation of energy, it's a box on bars that's dropped. I don't know what equation we use it. Number 5.
Use conservation energy to solve. A box starts at rest 30 meters above the surface of Mars. The box is dropped. What is the speed after falling 20 meters? All right, so as it falls, we're ignoring air resistance, of course. As it falls, what are all the forces acting on it?
Gravity on Mars.
Gravitational force.
Thank you, thank you. All right, so we got this gravitational force, or weight, because it's close enough, weight of acting on the box. So gravitational force and weight. Conservative forces or non-conservative forces?
Conserved.
Therefore, energy is conserved, and so the equation we're starting with here is that my total initial energy is equal to my total final energy. That's the equation we're working with. And as discussed over there, this energy is just kinetic plus potential. So I have my initial kinetic plus my initial potential is equal to my final kinetic plus my final potential. It's going to work this time. What's the formula for kinetic energy?
1/2
1/2
mv squared.
It's like doing it in rounds. Initial. What's the formula for potential energy?
Which one?
Thank you. The one associated with the conservative force in the problem. The conservative force is the weight. So what is the potential energy associated with the weight?
mgh. mgh.
And then just the same over here to final. And so now it becomes a plug and chug and figure out what you don't know. Because I think the question was find how fast it's going after it's dropped 20 meters.
Yeah.
Okay. So what's the initial speed? You're not sure. The box starts at rest. Okay? So that's 0, so there's no kinetic energy to start with. So it starts out with all this potential energy and absolutely no kinetic, and as it falls, it transfers between the two. Because it's a conservative force, the energy changes from one form to another. And this is what we're trying to find right here, this VF. So now the big question is height. What is the initial height? Because I give you 2 in the problem.
30.
Is it 30? You would also go in with 30? So let me read the problem again, if I may. A box starts at rest 30 meters above the surface of Mars. The box is dropped. What is the speed of the box after falling 20 meters? So we got Mars, box, 30 meters above it. And I'm asking, how fast is it going when it is now 10 meters above it? So if the initial height is 30 meters, what's my final height?
30 meters.
10
I
meters?
hope that means it hasn't gone anywhere.
Is it 10 meters?
It is. What else could you have chosen for the initial height?
0,
If the initial height is 0, what's the final height?
-20,
Okay? What else could we have chosen?
-10,
Okay? If the initial height is 10 meters, what's the final height?
-10.
There seems to be a pattern here. It really doesn't matter what you pick for the initial height, just so long as the final height is 20 below that. Typically, you pick numbers that have some meaning, so picking this to be 0 and the initial height is 30 and the final height is 20, perfectly fine. You save yourself just a little bit of math if you chose that to be 0 and this to be 20. Sorry, that final should have been 10 there. But the important thing here is the difference in the height, not the actual height itself. So the difference is what matters. So I give you the mass, I think. Didn't? Okay. Well, mass doesn't matter. So if I don't give you a mass, that means one of two things. It means either I made a mistake or it doesn't matter. So you could always ask, did you make a mistake? Did you mean to give us mass? And in this case, I don't have to, because it doesn't matter. In which case, you can either mathematically make mass go away, because every term has a mass in it, so it cancels. Or if you're not comfortable with that, make up your own mass. Because again, whatever you pick for the mass is not going to change the answer. Or it shouldn't. So I guess you started us off with this one. Do you have path forward on this? Or still have a question?
I'm still confused. Would you just plug in the G and the G?
So, all right, so mass I said didn't matter, so I'm gonna let it equal 1. G is, we're on Mars, so that was 3.7.
Yeah, 3.72, yeah.
Meters per second squared. Height, I was told 30 to start with. Mass, again, I just made up 1. G, still 3.721. And final height, well, if that's 30, this has to be 10. So whatever 30 times that is.
One eleven.
111.63 equals 1/2 times VF squared plus 37.21. That's the math problem you're solving. And again, wide variety of math backgrounds here. Some of you might be intimidated by it, but you're just peeling away the layers of the onion trying to get to the core. You're trying to find the speed right here, so you start getting rid of all the other stuff. So first, let's get rid of this thing dangling on the side here. So how do you get rid of something you're adding?
You subtract it from the other side.
Technically, from both sides. So that'll give you some number there. Then you're left with, on the right-hand side, 1/2 times VF squared. So now I've got this 1/2 here. So the question is, how do I get rid of the half? Aye? So divide by half, or
Times two, both sides. Multiply two times both sides.
either one works. And so you'll get something else, and so now you have a VF squared is equal to some number.
74.4.
This is 74 point,
Sorry, I need to multiply that by two.
Oh.
148.8.
and now you're left with, how do you get rid of a square?
Square root it.
You do the opposite, which is square root.
Okay, I was looking at my units and I was like, I don't know how these units will work out, but I didn't think about the square root. Like, I don't know.
Yeah, without the square root, this would be meter squared per second
Yeah,
squared.
so I was looking at that and I was like, I can use that. Sorry, I was confused.
Okay. Sounds like you're good now?
Yeah.
Alright.
I did that question with the gravity of Mars being 4.7, I rounded, or 3.7, I rounded it sooner, is that fine?
You did 3.7?
Yeah.
That's fine. You know, it's not a set number, just like the acceleration of gravity on Earth, and so 3 significant figures. Unless Mars is a perfect sphere, there's gonna be some variation.
Okay, I need help with number 7. I tried to watch one of your videos to let me click on it, but it's a 20 kg box sliding at 15 meters per second and a flat 15%.
The spring.
Yeah, the video would not let me click on it.
There was another video that was having issues. I didn't realize this was a problem, but on Blackboard, when you do a link and you put in the URL, if there's a space in front of the URL that's posted, Blackboard has no idea what to do with that. And so, there were 2 links that had spaces in front of the URL, which messed it up. So I apologize if there was a 3rd one that I missed. Alright, so 20 kilogram box, 15 meters per second, reaches a spring. Maximum the spring will compress. So in this case, let's think about what the forces involved. Force diagrams, you never quite escape them. So this box is moving to the right at some velocity, and there's a spring. And I think it's going 15 meters a second.
Yeah.
And the spring constant here is 30 newtons per meter. And what was the mass of the box?
It was 20 kg. 20 kg.
Okay. All right, so what are the forces that are going to be involved? I'm assuming it's a frictionless plane here, because otherwise I'd have to give you more information than what I gave you in the problem. And it would just be unfair for 110 to do that to you.
Yeah, frictionless.
Okay, so it's frictionless. So let's just take a look at it when it hits the spring. So we have still moving to the right, but slowing down. What are the forces acting on the box?
Wait. Normal force.
Wouldn't it be 2 normal forces?
There would. Call that Y1 and Y2.
And then whatever's push the box.
And what pushed the box?
We don't know.
The problem, in a problem like this, just assume the box came into existence already moving.
Okay.
What got the box up to that speed does not matter, because that happens before the problem starts.
Okay, so you wouldn't even include the force?
The force that got it moving? Yeah, the force that got it moving is long gone. What I came up with was the motion has no memory. So anything that's not happening during the problem is completely irrelevant. It does not affect us. All right, so this normal force right here, what I've labeled as Y1, what's causing that?
The ground, touching the ground.
Okay, so the box is touching the ground's pushing up on the box. What's causing this right here?
the spring.
So we actually have put a little S there. It's the spring force. It's an ideal elastic force, and I don't use a subscript E because I save that for electric force.
Is that other?
It actually is not an other.
Okay.
It falls outside of F-town, but we basically need a new letter there. F-towns. All right, so in terms of conservative forces, is weight conservative?
Yes.
Yeah. Is normal force from the ground conservative?
No.
Is the ideal elastic force conservative?
Yes.
I had a question on that, cause that's on our lab. What do you mean by that? Like,
By conservative,
yeah,
energy is conserved. That there are certain forces that allow energy to be conserved. There are certain forces for which there's a potential energy formula. So
so
that,
it has, so if it's conserved, it has it, but it's not using it?
conservative forces will take energy of an object and transform it from kinetic to potential or potential to kinetic.
Yeah.
So as it hits the spring and we get this elastic force being applied, that elastic force is causing the energy to change from kinetic into potential energy.
Yes.
I feel like I missed your question.
So is that what conserved means?
Conserved, yes. Usually conserved is worded as the total energy you start with is the total energy you have at the end.
So you said weight is?
Weight is a conservative force.
Because the weight isn't gonna change.
I hesitate to use that as the reason why. That the formal definition of a conservative force is that if I have an object moving from one point to another, if that, so say A to B, if I have that force acting on it, the work done by that force is the same regardless of whatever